Hello everyone. In this video, I'll be discussing the solution to a problem that was posted in Google group vlsidesignflow. So the question was related to synthesis of latch in Verilog. First, let us look into the question. So in this question, the RTL code was given. So in this RTL code, there is an always block, and inside this always block, there is an if else if block. And in this if else if block, it is written if a is equal to 0, then out should get a value of x, else if b is equal to 0, then out should get a value of y. And it was asked to predict the synthesis result of this code. And specifically it was asked that whether there will be any latch in the synthesized netlist and whether there will be any flip-flop in the synthesized netlist. So the short answer to these questions is that there will be one latch in the synthesized netlist and there will be no flip-flop. Just to remind you that latch is an level triggered device while a flip-flop is an edge triggered device. Now in this always block, there is no pause edge or nick edge involved, and therefore there will be no flip-flop in the synthesized netlist. But there will be a latch in the synthesized netlist. Why there will be a latch? We'll be seeing that in the subsequent slides. So just to show you, if we do the synthesis of this RTL, a commercial synthesis tool produced the netlist which is shown here. So in this netlist, there is a latch and there is an AND gate and there is a 2-to-1 multiplexer. And the schematic of this netlist is something like this. So there is a latch which is driving the output port out, and the data path of this latch contains of a multiplexer. The multiplexer selects between x and y depending on the value of a, and the enable logic contains an AND gate, right? Now in this particular case, the synthesis tool used a negative level triggered latch, meaning you see that there is a bubble here. It means that this latch will be transparent when the enable signal receives a value of 0. If the enable signal receives a value of 1, then this latch will hold the old value, right? Now let us understand that why the synthesis tool produced this kind of netlist for the given RTL code. Given this RTL code, its functionality can be conveniently represented using an 3x3 one-hot multiplexer. Now what is a one-hot multiplexer? So a one-hot multiplexer can contain n data lines and n select lines. Suppose these are your select lines and these are your data lines. Now out of these select lines, only one of them can have a value of 1. Rest all will have a value of 0. And suppose the third select line has got a value of 1. Then the corresponding data line, that is the third data line, will get selected. So this is what the functionality of one hot multiplexer is. Now given this if else if block, we can represent its functionality using a 3x3 one hot multiplexer. So for the first statement, if a is equal to 0, then out is equal to x. So we can write here that if a bar, meaning when a is equal to 0, it means a bar is true, then the first line, that is x, will get selected, right? And else if b is equal to 0, and this will be kicked in when a is equal to 1 and b is equal to 0, and we can write it using the term minterm ab complement, right? So whenever ab complement is true, then out gets a value of y. Now what happens if a is also 1 and b is also 1, right? If that is the condition, then none of this, if these conditions, either if or else if, will be executed, and in that case out will retain its previous value, right? And therefore we have the third select line. So the third select line is the complement of A complement plus AB complement, right? So A complement plus AB complement represent the condition in which either it will be written X or Y. And if we take the complement of that, it means that neither X is written nor Y is written to out, and out retains its old value, and therefore we have a feedback, and there is a and this feedback and retaining the old value represents that there is a something memory kind of thing, and therefore our synthesized netlist should contain a latch, right? So why do we have latch in the synthesis netlist? It is because that whenever this always block is executed, in some of the condition it retains the old value rather than being written X or Y, or the new value is not written to the variable out, but old value is retained, and retaining the value implies that there should be a memory element, and that memory element should be level triggered, and therefore a latch will be inferred in this particular case. Now let us understand that how the enable logic and the data logic will be inferred for this case by the synthesis tool. Now, using this function, we can understand that the out will retain its old value if A complement plus AB complement whole complement is true. And we can simplify this function by applying De Morgan's law in 2 times and then using distributive law. And this basically A complement plus AB complement whole complement is nothing but AB. Basically it will be true when both A is equal to 1 and B is equal to 1. That is the case when this out will not get updated, and that implies that the value will be out will be retaining its value, right? And therefore the function AB represents represents the function under which the out will retain its old value. And therefore what is the enabling condition? So the enabling condition is just the complement of the retaining condition, and therefore the enabling condition is AB complement, right? Now if the tool is using a negative level triggered latch, the bubble is already there, therefore on the enable side rather than AB complement we can simply have AB, right? Because this complement is already subsumed inside the latch, right? Now let us understand that how the data logic for this can be inferred. Now we know that the retention condition, whenever this A complement AB complement whole complement is true or AB is true, in that case latch is retaining its old value. Therefore whatever is being produced at the data logic under the retaining condition, that is immaterial, and therefore we can actually get rid of this, and we can think of these together, that whenever these two lines are 1, then Y will be produced and otherwise X will be produced, and therefore we can simplify this 3 cross 3 1 hot multiplexer to a 2 cross 2 1 hot multiplexer, right? So how to get from 3 cross 3 1 hot multiplexer to 2 cross 2 1 hot multiplexer? We have kept this A complement same. Whenever A complement is true, X is selected, and in other condition, that is whenever AB complement plus A complement plus AB complement whole complement is true, it will produce a value of Y, right? Because see, whenever AB complement is true, it should produce Y, and whenever A complement plus AB complement whole complement is true, the data logic can be anything. If we assume that it takes a value of Y, then we can take entire this function, and under whenever this is true, Y will be produced. And if we simplify this expression AB complement plus A complement plus AB complement whole complement, it will turn out to be A, right? And therefore, on the select line of this 2 to 1 multiplexer, there will be an A, right? Now, if we can see that when A complement is true, then X is selected, and when A is true, Y is selected. This is nothing but a 2 to 1 multiplexer, and therefore, rather than having one hot multiplexer, we can use 2 to 1 one multiplexer, right? Whenever A is true, Y is selected, else X is selected, right? Now we have got all the data logic and the enabling logic. We combine these two and we get the synthesized netlist, which was produced by the two. Now let us look into what could be a general approach for synthesizing if-else if block. Suppose we are given this if-else if block. In this if-else if block, depending on the conditions C1, C2, C3, Cn, the out gets the values D1, D2, D3, Dn. Note that all these conditions C1, C2 to Cn, these can be a Boolean variable or it can be a complex Boolean function. Right? Similarly, D1, D2, D3 to Dn can be complex Boolean function or it could be a simple Boolean variable. Now we can represent this functionality in a similar manner using n plus 1 one-hot multiplexer. So in this we have n data lines, right, and n select lines. And when none of them is selected, whenever, meaning that when if we take the NOR of all these things, right, whenever that is true, in that implies that the out retains the old value, right? So we have one more line, the line for retaining the old value. Now when will be a latch not needed in the synthesis? When it turns out that this retention function or the NOR of all this condition is actually boils down to 0, right? If the retention condition boils down to 0, then we need not retain the old value, meaning that either one of them, one of these conditions will always be executed, right? And how can we check that R is equal to 0 or retention condition is always 0 for what combination of C1, C2 to Cn? We can use what is known as BDD or binary decision diagram. Now what is a binary decision diagram? So it is a very compact way of representing Boolean function, and Boolean function is canonical using in a BDD representation, and BDD is widely used in logic synthesis and formal verification. Now using this BDD, we can easily infer whether R is boils down to or is a zero function, right? So if we build the BDD for R and if it reduces to a leaf node with label 0, then we can infer that latch will not be needed. A combinational logic is sufficient to model this if-else if condition, right? And sometimes what happens is that if we build the BDD for a Boolean function, the BDD may become take a large amount of memory, and we may not be able to represent it compactly using BDD packages, right? So in those conditions, we can use what is known as a SAT solver, which is more scalable than BDD. Now we can give this R function to the SAT solver, and if the SAT solver says that it is not satisfiable, meaning that under all possible combinations of Boolean variables R turns out to be 0, then we can infer that the latch will not be needed. It is the combinational circuit will be sufficient to represent this if-else if block, right? Now, once we know that latch is indeed needed for this if-else if block, right, then we can easily build the enabling logic, right? Enabling logic is basically the OR of these conditions, C1, C2, C3, Cn, right? And we can also get the data logic. We can synthesize the data logic by optimizing the logic representation of this n plus 1 one-hot multiplexer, and we can take this enable logic and the data logic through 2 level and multi-level logic optimization. And during this optimization, we can use that the R can be considered as don't care, right? Why? Because when R is true, the latch is holding its previous value, and therefore the data logic can produce anything, right? Or it is a don't care in that case. And we can use that observation to optimize data logic and get a better QR for our synthesized netlist. Once we have done the RTL synthesis and logic optimization, then the synthesis tool will do technology mapping, and it will map the synthesized netlist, which is in terms of generic gates, to the synthesized netlist in terms of the standard cells given in the technology library. So if you want to know more about these things, you can look into this book, VLSI Design Flow, Introduction to VLSI Design Flow. And to know, if you are interested in more questions on VLSI, you can join this group of this textbook, VLSI Design Flow. To join this, you can send an empty email to VLSI Design Flow plus subscribe at googlegroups.com. Thank you very much.